Good morning. I am Luyanda Noto from South Africa, and it's a great pleasure to present at Nono 17, which is presented by Africa Graphene. I am a researcher at the physics labs of the University of South Africa, and my research focus is on persistent luminescence and phosphors for solar cells and LEDs. And today's presentation is going to be more on persistent luminescence for home lighting. During the course of the presentation, I will discuss the importance of phosphors in the energy space, and from there onwards, I will elaborate more on the applications of phosphor materials in the space of persistent luminescence. For a moment, when the rest of the world had light, South Africa was in the dark. This was explained in terms of load shedding by our government. Now, a normal South African like myself still has no knowledge about the matter. However, what I do know is that there is a solution to all of this. We need to move off the grid. We need to harness energy that is reliable, like the sunlight. Let's mount solar cells on top of our roofs and generate electricity for ourselves independently. Let's incorporate solar concentrators into geysers and use them to warm water for bathing. Let's embrace new light bulbs which only rely on persistent luminescent mechanism. And the way to go about it, just using sunlight to switch on these bulbs. As indicated previously, persistent luminescence is the future home lighting solution which will only need sunlight to switch on. From there onwards, the bulb will continue to glow for a period up to 24 hours. The mechanism relies on trapping and gradual release of electrons, and this process will continue to last up to several minutes, continuing all the way to several hours. And during the course of this presentation, we will look into the electron trapping centers which are responsible for this persistent luminescence mechanism. Now, as we look into the dynamics of persistent luminescence, first we need to generate a phosphor by doping a lanthanide into a host material. Now, there are many choices of host materials. Our interest is in hosts that have a lot of electron trapping centers, which exist as defects inside the materials. Now, my interest has been on perovskites and composites of perovskites with spinels. Now, these materials have been garnets, titanites, tantalites, just to mention a few. A simple perovskite exists as an APO material with corner-sharing octahedral cages. Now, that houses the B ion and an inner octahedral which houses an A ion. They exist in cubic, tetrahedral, or orthorhombic symmetry. Now, for a big ion, the structure is cubic. Then, as the ion is reduced, the structure will move towards orthorhombic and eventually to a tetrahedral symmetry. Now, this happens because the structure accommodates the inner ion by collapsing the inner octahedral site by just simply tilting the corner-sharing oxygen cages. Now, there is an orbital overlapping that exists between the A and the B ion. Now, the collapse of the inner octahedral site will reduce the distance between the A and the B ion, and consequently, the stronger the overlap will be. Now, in the case when we excite the material, say using photons, electrons, or any other excitation source, then an electron will be shared between the A and the B ion. Now, due to the orbital overlapping that exists between the A and the B ion, now this is interpreted as a charge transfer between the two ions, and it will exist in a state which is simply called an intervalence charge transfer state. Let's consider a situation when an APO structure is doped with a PR ion. Now just looking at the electronic structure, we will have a charge transfer state from A, B ion electron sharing. Now IVCT, intervalential transfer, and the metastates of PR3+, the P, the D, and the H states, which are the most prominent in calcium titanate. Now for a cubic structure, the AB ion distance is greater, and consequently the energy is greater, such that the IVCT is well above both the P and the D states, leading to electron depopulation to both the P and the D state, now leading to both blue and red emissions emerging from these two states, form transitions of electrons moving from the P state to the H state, and electrons making a transition from the D state to the H state of plasmodium. Now, for an orthorhombic structure of calcium titanate, the IVCT is below the 000 state because the AB distance is lesser. So is the energy of the shared electron. Now, the IVCT will strongly couple with the P state, and all the electrons in that state will cross over to the IVCT. Now, from where they will de-excite to the D state and lead to a single red emission from a transition of D to H electron transfer. Now, experimentally, can we observe this charge transfer state? Yes. The diffuse reflectance of our sample shows an absorption corresponding to electrons excited from valence to conduction band in a region between 330 nanometers, right? And below that is a broad band corresponding to the gap. Within the gap, corresponding to the IVCT in a region of 360 nanometers. So yes, experimentally, we can observe the IVCT state. At room temperature, when we measure the optical response of our sample, we observe a single red emission from the D to the H electron transitions. Now this clearly proves the effectiveness of the intervalence charge transfer that exists in our material, which is orthorhombic. My interest in these materials has not only been in generating a single red emission, but also to enhance the persistent luminescence of the material. Now first, just looking at the electronic structure of calcium titanate, what we would have is a valence band, then we have a conduction band. In the valence band, we have all the localized electrons. Then in the conduction band, we have all the unlocalized electrons, meaning when we excite electrons, they move from the valence band to the conduction band. Now, in our material, which is filled with a lot of defects, we will then be having defects corresponding to calcium, and defects corresponding to titanium, and defects corresponding to oxygens. Now, those of calcium and titanium which are positive, they will lie in the donor level, and the corresponding vacancies will be at the acceptor level. However, both calcium and titanium, they are very deep into the band gap of the material, such that when we excite the electrons and they are trapped into the states, then they will recombine with the corresponding holes non-radiatively. And now the most important electron trapping centers for us will be those of oxygen. Now, because oxygen is negative, its interstitial defects will reside at the acceptor level, and the corresponding vacancy, which are positive, will be at the donor level. Now, this is very important to us in that these electrons which are trapped, they may be released back to the conduction band, depending on the depth of these oxygen vacancies. Some are deep, some will be shallower, close enough to the conduction band such that the electrons trapped can be stimulated back to the conduction band by the thermal energy of the ambient temperature. Now, that's very important for us in persistent luminescence. Now, our materials often, which we dope with praseodymium ions, which is now a luminescent center, upon exciting, some of the electrons will directly de-excite to the luminescent center and give us spontaneous luminescence. Now, in the case where we have shallower oxygen vacancies, electrons will take place in a mechanism, or rather a process, of electrons being stimulated by thermal energy of the ambient temperature to the conduction band all the way to the luminescent center, and now this opens up a channel which we call persistent luminescence. And in order for us to enhance this persistent luminescence, we need to go back to the structure of our material. Now, looking at this crystal structure, one needs to realize that I am looking at calcium titanate. It's calcium, it's a divalent ion, titanium, which is a trivalent ion, and oxygen. Right? Now, once we have something of that nature, it means my structure is only prepared to accommodate Ca2+, Ti4+, O2-. And in any case, if I were to disturb the stoichiometry, that will result in the material generating more defects. Now, in this case, I'm substituting Pr ions in the sites of calcium 2+ ion. What do we anticipate to happen? It's divalent substituted by a trivalent ion. Now, immediately there's going to be charge imbalance at a local site where I am incorporating praseodymium. And what will the material do? It will self-compensate by generating other point defects. Those will correspond to calcium, correspond to titanium, in order to balance this additional charge, which is positive. Now, if we generate calcium, we're generating defects which are not desirable, because all the electrons which are trapped there will de-excite non-radioactively. This is an effect we do not want. Now, what would I rather do in this case? What I would prefer is compensate for this charge imbalance myself, instead of having the material compensate for itself. Now, to do that, I want to remove the tetravalent and incorporate a trivalent ion, such that at a particular site where I will be having Pr, which is trivalent, and I will be having a trivalent ion inside the titanium ions. For an example, which we used in our case, was indium ions. I'm going to have indium, I'm going to have praseodymium ions. Now, it means at that particular local site where they are both opposite one another, the material will be charge compensated. However, there's a consequence which is accompanying this effect, in that I am now reducing the coordinations in the oxygen cage, and this will lead to one of the oxygen ions being knocked out of its position, leaving behind a positive oxygen vacancy, and that oxygen will move to an interstitial point position. And I'm happy with this because I am generating more oxygen vacancies, and which will take place in the phenomenon of persistent luminescence. The more of this electron trapping center that I can have, the longer the persistent luminescence in my material. Just looking at the decay curves of our materials, it clearly proves to us that incorporation of indium has an effect of enhancing the lifetime of our emission. In the case where we are looking at the decay curve with 0 more percentages of indium, we can clearly see that the decay of the emission is very fast and rapid towards 0. And in the case where we have indium ions, so we see that the decay is slowing down towards 0. Now this is an indication that incorporation of indium has been able, or rather effective, in enhancing the persistent luminescence of our material. Additionally, looking at these materials, we can do thermoluminescence spectroscopy to prove the existence of the defect inside the materials. Now, in this case, what we are looking at is we have electrons that were trapped into the material, and now after trapping these electrons, we then stimulate them using heat, and a technique which is required to do this is referred to as a thermoluminescence spectroscopy. Right? And what we would do is excite the material, allow all the photons to spontaneously de-excite. Now eventually all those which are trapped we can then stimulate out of the trap, now by just heating the material, and we would then record luminescence intensity as a function of temperature, and we would then have a spectrum which we refer to as a glow curve. Now in this case I have fitted my glow curve to give me several peaks, and to do this I need several other parameters in order to calculate activation energy corresponding to each thermal peak. However, in this case, my interest is not to look into that, but to show the effects of charge compensation in our materials. Now, this would be a material without a charge compensator. Now, let's see what would then happen in the case where we're incorporating charge compensators into our material. And there we are, a material which has been charge compensated. We can clearly see the effects. Looking at the overall glow curve, the pink is now extended towards lower temperatures. We can see there's a new peak which has been generated, now adding to the previous peak which was measured for a material without a charge compensator. So what is this telling us? We are generating more electron trapping centers which are closer to the conduction band. These are shallow electron trapping centers which participate in the phenomenon of persistent luminescence. Now, also proving the effectiveness of charge compensation. We are aware that we are developing a material that will be working outside environment. If we were to take our phosphor, a persistent material, generated into a globe, it can be a globe or a thin film, but eventually we have to put it outside, expose it to the sunlight, and environments are harsh out there. We have corroding gases of materials, so we need to ensure before we can use a material into these devices that it is actually chemically stable. And the way to go about it is rapidly age the material using an electron beam. And the way we went about it was take a sample, put it inside a vacuum chamber, then mount a CL spectrometer onto the chamber so that we can monitor the CL intensity changes upon exposing our sample into prolonged electron beam. Now, we know that in our chamber we have oxygen, which we will be having also in the real environments. We have water vapor as well. Now, what we then went on to do was backfill oxygen, put an oxygen filler next to the sample so that we can have an electron beam interacting with the oxygen and splitting it from oxygen molecules to oxygen atomic species, which are very reactive so that they can attack the surface. In so doing, we are rapidly aging our material. Upon bombarding the surface with electron beam, we then measure an OJ spectrum and monitor all the electrons which are emerging from the surface. Looking only at the OJ peaks, we can then determine the elements which were on the surface, and in this case we had oxygen, we had calcium, and we had titanium, and we are then measuring the OJ peak-to-peak heights over a long period, and at the same time we are monitoring the change in the CL intensity, which is marked with the blue line in our spectrum. Now I am looking into these profiles. Now I can see the change that over a long period, titanium is remaining constant, calcium is remaining constant, and I see that oxygen is increasing up to about 500 electron doses, and then it begins to become stable and remains constant as we increase the time. At the same time, we also realize that the CL intensity is also decreasing rapidly to about 40% of intensity and begins to stabilize around 500 electron doses as well. Now, this is a clear indication that there is a new species which has been formed on the surface, now which is quenching my luminescence intensity. Now, comparing the spectra before and after I exposed my material to a prolonged electron beam, I see that the CL intensity decreases from about 150 counts to about 50 counts. Now, this is clear evidence that the luminescence intensity has decreased, and we need to look into the species which are now forming, which are resulting into this quenching of the luminescence. And to do this, we have to do XPS measurements. Looking at the XPS peak, only focusing on the oxygen peak, the 1s of a material before I expose my material to the prolonged electron beam, and also the oxygen of the material which I prolonged into the electron beam. Now, I just simply refer to them as degraded and undegraded, or before degradation and after degradation. Now, after degradation would indicate a material which was exposed to a prolonged electron beam. Now, I'm looking at the binding energies of the material before degradation. Now, what do I see? I see from oxygen peak is a major contribution which is coming from calcium titanate, which is the major material inside, which is the major material on the surface. And also I do have some suboxide which are forming. I do have Ti, which is possibly an unreacted titanium when we were preparing the material, and also I do have some calcium hydroxide as a result of water vapor also attacking the surface, and I do have the rest of the species. Now, my interest is more on what is happening after I prolong my material into an electron beam. Now, what I see immediately from the oxygen peak is that the peak is broadened to accommodate an additional peak at lower binding energies. And when we feed, we realize that we are forming calcium oxide, and consequently we realize also the intensity of the calcium peak is reducing with respect to the ratio of titanium calcium. Now that reduced ratio, it indicates to us that we are forming more of titanium, we are forming more of titanium dioxide, calcium oxide, calcium hydroxide, and the others. Now, we can clearly see from this, we have formed new oxides, and they are an agent for quenching our luminescence intensity. To sum up the process which has taken place during the degradation process, now we had a sample which is calcium titanate, and we had an electron beam, and we were backfilling oxygen close to the sample such that the electron beam was dissociating the oxygen molecules into atomic species which are attacking our surface. And from the APPH profiles, we could see that the luminescence intensity decreased rapidly, and now XPS measurements, they are now confirming to us that yes, we have an agent which is acting, or rather a new oxide which is forming, which is calcium oxide, titanium dioxide, which is also increasing on the surface, and also a suboxide of calcium. Now, when we do the Monte Carlo simulations, which we are not covering in the presentations, we pick up that at the interface of the new oxide and exactly our sample, we have a defect which is forming, which is acting as a quenching center, which is now the exact agent which is now promoted by the formation of the new oxide layers on top of our materials, which consequently quench the luminescence intensity in our materials. Now, if we are going to work on a general remark, if we are going to work with phosphors which will be out in the environment, it is always best to work with a phosphor which is chemically stable. And in our case, we can see that the sample which we are working with, it's not as chemically stable as we would love it to be. Now, for future studies, we will be looking into different ways in which we can improve the chemical stability, or maybe we can find a coating layer which we can use to coat our material in order to prevent the degradation process which may take place in this case. To sum it all up, I would say that I have undergone an investigation of selecting perovskites and composites, and I've investigated the effects of charge compensation. I have also looked into the matrix effects of fluxing agents, or rather using charge compensators to try and enhance the persistent luminescence. And I have also investigated the chemical stability of my material by rapidly aging the surface using electron beam and backfilling with oxygen. And what I have achieved out of the entire study is I was able to generate a pure red emitting phosphor. I was able to enhance the persistent luminescence. I then was able to probe the chemical stability of my material in order to know that in the future I will then be in need to protect the surface of the material better. Lastly, I would like to thank everyone for taking time to listen to my presentation, and thank you for the funding coming from the National Research Foundation and DST. And also thank you to Africa Graphene for the platform. It was a great pleasure to take part in Nano 17. Thank you.